Okay, hello and welcome to Inverse Laplace Transforms lecture number 2. Now, we looked at the first type of inverse Laplace transform yesterday, and that was when you could factorise the quadratic term in the bottom of the fraction you're looking to inverse transform. Now, the second type is going to involve completing the square, but what I want to do is just remind you how to complete the square. Right? So, if you've got x squared plus 4x take away 12, then you want to create a square bracket like that, and the take away 12 goes to the end. Now what you want to do is you want to put x into the bracket, because x squared gives you x squared, and you halve the number that's in front of x in the middle, so that's 2. Now if you were to multiply out the bracket x plus 2 times x plus 2, you would end up with x squared plus 4x plus 4. Now you get that plus 4 because you've always got to take away whatever number you put in that bracket squared. Which gives me x plus 2 squared take away 16. Okay, and if you were to multiply out that bracket and take away 16, you'd end up with that number that you started with there. 2. So, if out your square bracket, plus 20 goes to the end. Now, you bring the x down to give you x squared, and you halve the number that's in front of the x, which would give me negative 4. And you take away on the outside whatever number you just put into the bracket squared. Now, because that when you square a negative, you always get a positive, it's always going to be take away whatever that number is in the bracket, so you don't need to worry about whether it's a negative or a positive in here. So that gives us x take away 4 squared plus 4. Okay, now obviously we're going to be doing it in terms of s rather than in terms of x, because we use s and t for Laplace. So I'll just do one with s to show it's the same thing. So s squared take away 16s plus 140. So, set the square bracket, move the 140 to the end. You bring the s down and you halve the number that's in front of the middle s. And you take away the number you just put into that bracket squared. So that gives me s take away 8 all squared, take away 64 plus 140. And I said that bit there is always going to be a subtraction, it's always going to be a takeaway. And we get s take away 8 squared take away 76, if I can do basic arithmetic. Right, so if you want, this is a wee bit of practice. Okay, so by yourself, can you please try those ones? And if you pause the video there, the answer is s plus 5 squared, subtract 5, and as I said, the 5's and the s's are going to look very similar. Try and find a way of making them look different. Then s take away 8 squared plus 36. So there we go. those are our answers. Right, so let's have a look and see what this is actually used for then. Right, now this is type 2. This is inverse Laplace transforms type 2, right? This is when you have a quadratic on the bottom of the function you are looking to inverse that has 3 terms, in fact cannot be factorised. Let's try and explain it so that it works for all of the ones that we're going to get right. So this is type 2 is when you have a quadratic, so something with an s squared in it, on the bottom of the function you're looking to inverse transform, and that has both an s and an s term in it. Right. Again, sounds quite tricky, but it's actually fine. Right, so example 1. So we have f of s. So example would say find f t. So that just means find the inverse transform. So capital F of s is 2 over s squared plus 6s plus 13. Now, what we know is, because that's a trinomial, if we go to our Laplace transform table from our booklet, we don't have anything in our booklet on our table that deals with something like that, right? Nothing at all. None of these, the bottom of any of these functions looks like s squared plus 6s plus 13. So, remember what we try and do first. We try and do c dt, right? So, you're adding to make 6 and multiplying to make 13. So they're both plus, they're both minus, and the only way making 13 is 1 times 13. Now, I try all the different combinations. There is no way of me making 6 from those combinations. So it doesn't factorise, right? And remember, the way you can check is if you do b squared take away 4ac, you'll get a negative number or a number that's not a square number. But hey, you should be able to spot from that whether something factorises or not. Right, so that means I've got to complete the square on the bottom, just like I did. So I set up my square bracket, and I move my 13 to the end. So the s comes down, and you half the number in front of the middle term. You take away that number squared. So just exactly what we did in the previous page. Right, so it doesn't factorise, so complete the square. Right. I'm left with that there. Right, so I'm left with 2 over s plus 3 all squared plus 4. Right, now, I then look at my Laplace transform table. Right, now, because I've completed the square, I'm going to then have to use inverse first shift theorem. Right? And what that means is you know that whatever's in the bracket here that you've completed the square with is then going to be on the outside of the bracket underneath, right? So let's show that. Right. So what I'm going to do is I'm going to then rewrite that. Whatever that bracket was, it's become an S. We see it as s plus 3 becomes s. Right? And then look at my Laplace transform table. I'm looking for s squared plus 4 on the bottom. Right, so I'm looking for s squared plus something. Right? So s squared plus something is either this one here or this one here. Right? Then I check, does it have an s on the top? No, it doesn't, so it has to be sin. So it's going to be that one there. Right. So the first thing I need to do is rewrite the bottom. Like that there. So you always write it so it matches exactly the transform from the table. Now, if I look at the table, that means that that transform there is sin 2t. Nope, sorry. I forgot to write inverse Laplace transform here, didn't I? So I'm going to go into that here. Should have probably done that earlier on, but it doesn't make a difference. This whole first step is just putting in the right format, so I could do the inverse transform. Right, so that means that f of t is sine 2t, but remember I've got this, it's s plus 3 equals to s. Now that's the opposite of the first shift theorem. So this bit always becomes an exponential, and it's the opposite of that number there, so it's negative 3t, and it multiplies sine 3t. So the inverse transform of 2 over s squared plus 6s plus 13 is e to the power of negative 3t sin 2t. Right, these ones are tricky. I know they're tricky. So we need to do a few more examples to make sure that we are getting them and understand what's going on. So okay, example number 2. So we're going to find f of t. If f of s is s plus 7 over s squared plus 2s plus our favourite number in this, 5. Okay, so this is probably, but again I would do CTT. Right. So I'm adding, make plus 2, and I'm multiplying to make plus 5. So they're both plus, they're both minus. The only way I'm making 5 is 1 times 5. Well, none of these combinations are ever going to make 2. It doesn't factorise. Okay, so we then need to complete the square in the denominator. So I set my square bracket, I put my plus 5 to the end like that. So you bring the s down and you half the number that's in front of the middle term. You take away the number you just put into the bracket, squared. Which gives me that term there. Right, now I'm going to say I'm going to inverse Laplace transform it. Right. I said you could have done that at the start, you could do it anywhere, it doesn't matter as long as you note somewhere that that's what you're actually doing. Okay, so this bit's going to become f of t. Right, now remember I've completed the square, so I need to make all my s is s plus 1 because I want to make s plus 1 go to s. Right, that means I need to make an s plus 1 up here too because it's s on the top and s on the bottom. Right, so I need to make that s plus 1. Right, that's what I want it to look like, right? So I need to make these two things the same because I'm not actually doing anything to them. So s plus 1 plus what gives me 7 plus 6. Okay? So now I can do my first shift theorem. That's going to be s plus 6 all over s squared plus 4 squared as s plus 1 becomes s. Like that. Okay, so I've completed the square. Then I know that I need to make the bracket that I've completed the square in s rather than s plus 1. But in order to do that, every single place that I see s in must be s plus 1. So, next step is we look at the bottom of our function in the square brackets and see, right, well, the bottom of it looks exactly like, again, like sin or cos, right? But sin and cos don't have s plus a or s take away a. They've just got s or they've got a. So I know I'm going to have to break it into two separate fractions. Sorry, where's that got squared on it? I shouldn't have, sorry. Okay, so you can see there that I've split the top of the fraction. That was a wee mistake. Just to be typo from me, right? So I've split the top of the fraction there, right? And now we've got something that pretty much looks exactly like a thing from a table, right? So I need to make the bottom bit squared. So it's going to be s over s squared plus 2 squared plus 6 over s squared plus 2 squared. So s plus 1 goes to s. Now, what I know is that I need to make that 2. Right, so that needs to be 2 over, right, in order for that to work. So let's put a 3 there, like that. Okay, so just remember those two numbers need to be the same for it to be sin. So let's do the inverse Laplace transform. So that gives me cos 2t. That there in the bracket gives me sine 2t. Because s plus 1 goes to s. So I've got cos 2t plus 3 sine 2t. S plus 1 becomes s. And therefore this bit here becomes e to the power of negative 1t, which is e to the minus t. And it multiplies both things. Like that. So that is the final answer to your inverse Laplace transform of s plus 7 over s squared plus 2s plus 5. After you have went through that, had a little look at it, can you please try question 6 on page 29? I know the light levels keep changing, the light in the camera keeps on coming on and off. Right, now after you've done that, you can also try from this page here, question number 11, that one there. 4s plus 2 over s squared plus 6s plus 34. Again, it's of that type. And the answer you should get to that is question 11 here. The answer there. Okay, so can you please attempt those two questions for me? Right. Move those over to one side. So inverse Laplace transforms. This is the last type, and this is type 3. Right. So this is when we have to use the last bit of partial fractions knowledge, right? So this would be the last one you would ever look for, right? And this is, you cannot factorize or complete the square on a quadratic on the bottom of the function, you are looking to inverse. Okay. Now you can normally tell, because it's got a bracket like a squared plus 10 and a bracket. Something like that. Now remember, if that was a subtraction, you could do difference of 2 squares, so you could factorise it. Right, so it's only if it would be an add, right? Right. Example number 1. Now, what I want to do by the end of this is make sure that you can do every single question on that page 29 on inverse transforms, because that's a kind of good target for us for the end of this week. So, find f of t. Right. So, we look at our function. Right, we see we've got a quadratic term it's got the s squared in it, and that cannot be factorised. There's no way of factorising s squared plus 4. There's no common factor, it's not a difference of 2 squares, it's not a trinomial. You also can't complete the square because there's no middle s term. So factorising, so c dt cross complete the square cross. Can't do either factorising or completing the square, right? Which means it's a more difficult partial fractions. This is an irreducible quadratic factor partial fractions question. Right, so, and we did this in engineering maths 3. So partial fractions is the name of the game. So I know I can't factorise it, so it's got to stay the same. So it's going to be partial fractions, but it's the one with the irreducible quadratic factor. Okay, so let's rewrite it. Right, now, that's a normal factor. So for a partial fraction, we just write that as a over s plus 1. Right, now, your second bit on the bottom is going to be s squared plus 4. Now, if you remember, the degree between the top and the bottom must be a difference of 1, right? So I can't put b up there, because it needs to contain an s. So I need to put bs plus c up on the top there in order to make that work. Okay, so we did that in engineering 3. We did it quite a lot. Right, so now, just like in other partial fractions questions, we want to multiply through by the denominator. 3s squared plus 2s plus 4 equals a s squared plus 4 plus, and watch this, make sure you put the bs plus c in a bracket, s plus 1. Okay, now I think that makes it a bit easier. Now what you do is you see, right, I can't make that bracket 0. There's no number that can ever make that bracket 0. I can never make that bracket 0, but I can make that bracket 0 because I can choose s to be -1. So let's do that. Try and make any of your brackets 0. So 3 times -1 squared plus 2 times -1 plus 4 equals 8 -1 squared plus 4 plus, that's just going to be 0, isn't it? So 3 plus -2 plus 4 equals 8 of 1 plus 4. That whole bit's just going to be 0. So 3 take away 2 is 1 plus 4 is 5. Right. So 5 is 5a. That just tells me that a is 1. Okay, now that's all you can do in terms of making bracket 0. So what we have to then do is, I'm just going back up to this line here so you can see where I was. Right, so you've worked out that bit here, and I'm going to go back up to that equation just so you can see it, so that we can do work with it. So what we're going to do is equate coefficients. We have done this before. Equating coefficients. So you're going to multiply everything in this side of the equation. Right, so that's going to be a squared plus 4a plus, right, that multiplied by that is bs squared plus bs plus cs plus c. Simple as that. You just multiply that original equation. Now what you're going to do is you're going to compare the terms. So we've got an s squared term, we've got an s squared, and we've got a number term. Right, so we're first going to equate s squareds. So we look at the left hand side of the equation, we look at the right hand side of the equation. Right, we do this for all of them when we're equating coefficients. Right, so on the left hand side of the equation, I've got 3s squareds, so that's 3. On the right hand side of the equation, I've got a and b, so a plus b. But I've already worked out that a was 1 previously, so that's great news. So 3 equals 1 plus b. That tells me, I'll just write it over here, that b is -2. Right. Now choose the next one. Right, I'm going to look at s's. Right. Right. So on this side of the equation I've got 2 lots of s, so 2. On this side of the equation, when I multiplied it all out, I've got b and c. But I already know that b is 2. That tells me that c there is 0. And if you want to check it, you could check the last bit and see if it makes sense. Well, 4 should equal 4a plus c, and it does. Whatever. Right, so that means we can go back up to our partial fractions. So this is our partial fractions here, right? And we've worked out in our partial fractions that a is 1, b is 2, and its c is 0. 3s squared plus 2s plus 4 all over s plus 1 s squared plus 4 equals 1 over s plus 1 plus 2s over s squared plus 4. You could write 2s plus 0 if you wanted. There we go, right. So now what I want to do, so this is f of s. Okay. So I now want to find the inverse transform of this. Right, now we've got two separate fractions. You could just do it separately if you wanted. So it's the inverse Laplace transform. 1 over s plus 1. And I could take that 2 out, so that's 2 times the inverse Laplace transform s over s squared plus 4. Okay, so that just becomes f t. So as usual, the inverse Laplace transform of capital Fs becomes ft. This here just becomes e to the power of negative t. Right, I've got to try and sort this one out before I can do it, so that's going to be s squared over s squared plus 2 squared. And that is now exactly the one for cos 2t. And that is how you find the inverse Laplace transform when you cannot factorise and you cannot complete the square in your Laplace transform. Right, so after doing that, you're now going to be able to do question 5. Now the one thing you've got to watch about question 5 is that there's a repeated linear factor there as well. So when you're doing your partial fractions, you're going to get a for s take away 1 plus b for s take away 1 squared plus you're going to get cs plus d over s plus 4, like that. And then you would do your partial fractions like that. So that might actually be a wee bit more difficult, but try it. The answers are at the back of the booklet as usual. Right. Also, another worksheet. There's all these questions you could try and you should hopefully be able to have a go at now. Right, now they are decent questions. We're going to have to factorise them, not factorise them. For example, that there is a tricky one. That there, you've got to factorise it common factor first, then trinomial, then you'll find it's an irreducible quadratic factor. It's a good question, that. That again, you can factorise that using s cubed, but then you're going to get a repeated linear factor of a cubic. Okay, this here you can't factorise. It's going to be interesting to see how people maybe attempt that one. Okay, and then you've got that one there. Now, the answers for those questions 11 to 19 are there. Now, as you can see, this has been taken from someone who made these questions up and put them online. They're not anything that I've made up myself. I just found them and I thought they would be helpful for our class. So thank you to whoever's made up this sheet. Okay, so can you please have a go at those questions and let me know how you get on and see if you need any help. Thank you.